screencast goes over the solubility equilibrium homework. So in problem number 1, I asked you to write a balanced dissolution equation. So I just wanted you to represent how solids split into ions in water. Now I asked specifically for the saturated solution, and that's because when an aqueous solution is saturated with the solute, the rate of dissolution, so the rate of splitting up into ions, is equal to the rate of crystallization, where it's getting back, where those ions are getting back together to form the solid. And so we're going to be dealing with equilibrium here. A lot of these have to deal with slightly soluble salts, and we have, with our solubility rules, called these insoluble because they don't really dissolve a whole lot, but they do dissolve some, and it's just a tiny amount. So that's really what we're dealing with mostly in this chapter, is how much will actually dissolve of that tiny amount. So 1A, we're talking about chromium carbonate, so you had to write that formula correctly there. It is going to split up into chromium ions and carbonate ions. And again, we should see ions over here. Don't split up a polyatomic ion. It is a double-headed error because at a saturated solution, both reactions would be happening. This would be splitting up at the same rate that this would be getting back together. The next one is silver bromide. So we have our ionization equation there. Next we have calcium phosphate. Here we had to deal with balancing the equation. It's going to be 3 calcium ions and 2 phosphate ions for every one of these that is splitting up. Iron 3 hydroxide looks like this. Again, we've got a solid over here and aqueous solutions of these ions over here. We do have a coefficient for this one as well. And potassium sulfate. Now, A through D were all slightly soluble salts. If you were to look them up on your solubility rules, we saw that all of these were insoluble. Potassium sulfate's a little different. It is very soluble, and so this reverse reaction, it's not going to build up until this thing really hits its saturation point, and we're going to have a lot of ions. So when we go to writing equilibrium expressions, which is next, this one is going to have a very large K value, whereas all these others will be very small. Alright, so then I ask in problem number 2 to write the equilibrium expressions for each of the salts based on their dissolution equations at equilibrium. So it's the same thing as we've done before, so K equals, and it's products over reactants. The only thing is that our reactants are solids, so they drop out of the equilibrium expression. So all we have to deal with are the products. Now they should be raised to their coefficient power. So we call it KSP, but we'll get to that in a little bit because it's our solubility product. You could just write K. For chromium carbonate, it just looks like this. We have 1 ion of each. Silver bromide looks like this. The equilibrium expression for calcium phosphate looks like this. You have to raise them to the coefficient power. Iron 3 hydroxide and potassium sulfate. Alright, on the back, we're dealing with Le Chatelier's principle, and in that one, we're going to, I gave you a equilibrium expression of magnesium hydroxide. It's going to split into magnesium ions and hydroxide ions, and then again, this would be a slightly soluble salt. So we're just going to look at what might happen. If we add magnesium to ions, add shifts away, so we're going to be making more of that solid. If I add more solid magnesium hydroxide, there's going to be no effect because solids do not affect the equilibrium position. If I add more hydroxide ions, so add some base to this, it's going to force the reaction in the reverse way, and we'll end up with more of that magnesium hydroxide. If we add, or if we remove some magnesium ions by adding sodium carbonate to the solution, So we're going to remove, and remove shifts towards, so we are going to be favoring that forward reaction. The carbonate is going to combine with the magnesium to form an insoluble compound. Hydroxide ions are removed by adding hydrochloric acid to the solution, because the hydrochloric acid would neutralize the base, therefore removing it and force the reaction in the forward reaction. Alright, so I ask you about the net ionic equation for the substances mentioned in your explanation for each of the following. So why does adding sodium carbonate reduce the concentration of magnesium ions? That is because magnesium carbonate would precipitate, decreasing the concentration of those magnesium ions. It's going to take those ions out of solution, just like we saw when we added that silver nitrate to our equilibrium expression, making it go from pink to blue and back and forth. So the net ionic equation for that, the magnesium ions are going to interact with the carbonate ions and form that solid magnesium carbonate. Then why does adding hydrochloric acid reduce the concentration of hydroxide ions? It results in the formation of a weak electrolyte, decreasing the hydroxide ions. It neutralizes that hydroxide, and so your net ionic equation would be OH negative plus H plus from that hydrochloric acid is going to give you water. Okay. I hope that helped. We'll learn some more about the solubility product KSP.